This is the first gear wheel without teeth that works only with fluid and without contact. A research team has developed a gear wheel in the laboratory that transmits rotational movements using only fluid. They use the clever physics of hydrodynamic interaction. Gear wheels have been used in almost all machines for centuries, but in extreme situations such as space or the deep sea, they are sometimes simply too prone to failure. And yet they have been used for 2000 years. But that could change now. Find out how the liquid gear wheel works, whether it will soon be used in our cars, and what the competition is like. And with that, welcome to the German Science Guy. I'm Dr. Jakob Beautemps, and in Germany we say Los geht's! Gear wheels are an integral part of our everyday lives. In wristwatches, car engines or bicycle gear shifts, everywhere teeth mesh together to transmit power. Without them, our technological world would literally come to a standstill. The cool thing about it is that the principle is really old. It is believed that as early as 3000 BC, Chinese chariots used complex gearboxes to maintain direction. Even one of the first analog computers for astronomy from the late 2nd century BC was built in Antikythera, based on gears. In fact, it took humanity more than a millennium and a half to come close to reaching this level of technology again. But actually, the physics behind gears is simple. They transmit rotational motion. If two wheels are the same size, they rotate at the same speed, only the direction is reversed. If there are different sizes, a transmission ratio is created, with a small wheel rotating faster and the large wheel slower. But gears have one major problem: they need contact. The teeth, whether made of wood, metal or plastic, must mesh perfectly. And where there's contact, there's friction, which means heat, wear and maintenance. In extreme situations, such as in space, in the desert or in the deep sea, classic gearboxes therefore reach their limits. This is precisely why researchers are continuing to search for contactless alternatives. And a team at NYU has now achieved something completely new: a liquid gear wheel. They have developed a gearbox that does not need teeth, but instead uses fluid vortices. You can imagine it like this. In the laboratory, there are two cylinders in a basin filled with a thick liquid, a mixture of water and glycerine. One cylinder is driven by a motor. It does not touch the second cylinder, but as soon as it starts to rotate, the second cylinder begins to rotate with it. The secret behind this is hydrodynamic interaction. This is the same effect that can be observed in schools of fish. A fish swims, it moves the water around it, and this current in turn affects the other fish. In the case of the gear wheel, the fluid now takes on the role of virtual teeth. But that's not all. The team has discovered that the type of transmission can be controlled without modifying the gearbox. There are two modes. The classic mode kicks in when cylinders are close together. The second cylinder then rotates in the opposite direction to the first, just like a normal gear. The second mode is belt mode. If you increase the distance or speed of the first cylinder, something crazy happens. Both cylinders suddenly rotate in the same direction. This then works like a conveyor belt or a belt drive. Incidentally, this also happens when the cylinders are very close together, so when there is virtually no fluid between them. This means that the direction of rotation can be changed on the fly simply by adjusting the distance between the cylinders or the speed. To make this visible in the laboratory, the scientists use tiny air bubbles and light, which makes the flow patterns appear as glowing lines in the water. Now, some of you will say, Jacob, transmitting force through fluid, we've had that for a long time. And yes, you're right. The concept of transmitting force with fluid is nothing new. In technology, and especially in automotive engineering, we have been using it for a long time under the term fluid technology. A classic example is the viscous coupling in a wheel drive system. These consist of stacked discs in viscous silicon oil. When one side rotates, the oil's viscosity pulls the other side along with it. The key feature of the NYU research, however, is that it does not require a narrow gap or sticky oil, but instead uses free vortices in an open basin. Another example that already exists is particularly relevant for automatic transmissions, the hydrodynamic torque converter. A pedal wheel transfers oil to an opposite wheel, causing it to vibrate. Here too, the metal parts do not touch each other. However, these systems require complex, permanently installed pedals to direct the flow. And then there are magnetorheological fluids. These are fluids in which tiny iron particles float. When a magnetic field is applied, these particles immediately arrange themselves into rigid chains and the fluid solidifies in milliseconds. This allows couplings or brakes to be built that can be controlled with extreme precision. But here's a crucial difference. All these systems require complex, permanently installed blades, lamellas, or even magnetic fields. The NYU team has managed to do all of this without the complex system. They use only smooth cylinders and pure fluid dynamics to generate these two modes, which is really fascinating. That's what I call the advantage of simplicity. But if it's also simple, why don't we convert every transmission right away? The magic word is efficiency. And that brings us to the big hurdle of this video. You know the drill, subscribe to the channel and activate the bell so you don't miss any more videos. And if you'd like to support my work and get some behind the scenes impressions, you can also become a member of this channel now. And now we start with a deep dive into the hurdles of this new technology. Okay, let's talk about efficiency. With a classic mechanical gear, it's around 98%. That means almost all of the energy gets where it's supposed to go. With systems based on fluids, it's different. They have slippage. This means that the fluid simply slips through under load and some of the energy is converted into heat. The problem? The paper did not address when this point is reached. When liquids are constantly swirled, internal friction generates heat. One might think that the problem would be solved by eliminating direct contact, but the heat causes the liquid to become thinner, so its viscosity decreases and the power transmission becomes unstable or even breaks down. The study clearly shows that efficiency is extremely dependent on the Reynolds number. This is a ratio between the inertia and viscosity of the fluid. If the speed, this is omega in the formula, is too low or the fluid is too viscous, no stable vortex structure forms to move the second cylinder. At high speeds, on the other hand, the fluid begins to escape due to the centrifugal force, which then reduces efficiency again. But there are more points we have to talk about. The liquid gear operates in an open basin and the cylinders are smooth. This means that slippage is significantly higher than in blade-based systems or in the rigid transmission of normal gears. And then there's competition. We've already looked at a few other transmissions that use fluid, but that's not the only way to prevent mechanical friction. There are also so-called magnetic transmissions. These use magnetic fields to transmit power without contact. If you are interested in more details, please write it in the comments and I will make a separate video about it. Magnetic transmissions are already established in industry, they are low maintenance and also have overload protection. If it gets too heavy, the magnetic field simply slips through without anything breaking. But more on that in another video if you want it. And by the way, many of you requested a video on an anode-free battery, so the video will come in the next few weeks. I'm already working on it, so be sure to subscribe. In the end, I can just say about the gear without teeth, it's very interesting from a physics perspective, and that's my background and where I did my PhD, and so I am really interested in it, but it's definitely a niche and nothing for our cars. But especially in space travel or in deep sea technology, it still can become interesting. But what do you think? Be sure to write your thoughts in the comments, and with that I will say see you next time, take care, or as we say in Germany, bleibt gesund, your Jacob.